Welcome to section 8.3. In this section, we're going to look at more graphs and then shifting of graphs. So before we can look at shifting of graphs, you need to have an idea of the basic shape of some of these common graphs here. So the first thing I want to graph is f of x equals x. Okay, I'm going to essentially just plug in numbers in my head and graph them here. Okay, if x is 0, f of 0 would equal 0. So it goes through 0, 0. If x is 1, f of 1 would be 1. If x is 2, f of 2 would be 2. F of x and y is always the same as just x. So you're getting points all in a line. So f of x equals x is a basic line. This particular line has a slope of 1 and it goes through the origin. Okay, imagine that I drew that perfectly straight. Alright, there's f of x equals x. F of x equals x squared is very similar to the one that we drew in the last section, which was the negative of x squared, but this time we just don't have that negative. So if x is 0, y would be 0 squared, or 0. If x is 1, y would be 1 squared, which is 1. If x is 2, y would be 2 squared, which is 4. So 2, 4 is on the graph. And if x is 3, y would be 3 squared, or 9, which is off the chart here. Okay, let's do some negative values. F of negative 1, well, negative 1 all squared is negative 1 times negative 1 is positive 1. Negative 2 all squared is positive 4. And so you can see the pattern here. Negative 3 squared is also 9, which is off this grid. All right, and it has this basic shape. A parabola that opens upward. Okay, square root of x. Now, as we learned in the previous section, you cannot take the square root of a negative number, and because this is just a simple function, just square root of simply x, we can't plug in a negative number for x, right? If x is negative 1, you would have the square root of negative 1, which is undefined. So the smallest x value we can plug in is 0. And the square root of 0 is 0, so this goes through the point 0, 0. Next, if x is 1, the square root of 1 is 1, so it goes through the point 1, 1. If x is 2, the square root of 2 is about 1.4 or so, kind of right in there. If x is 3, square root of 3, I don't know off the top of my head, so let's jump to the square root of 4, because the square root of 4 is 2. So 1, 2, 3, 4, 2 is on this graph. And you get the idea of basically the shape of the graph. Looks like that. Okay, it doesn't actually flatten out ever. It actually does keep going up forever and ever. Alright, absolute value of x, we learned in the last section, has a V shape. So let's plug in some positive and negative numbers. We'll start with positive. Actually, we'll start with 0. Absolute value of 0 is 0. Absolute value of 1 is 1, so it goes through 1, 1. Absolute value of 2 is 2. Absolute value of 3 is 3, so on. And then if x is negative 1, the absolute value of negative 1 is positive 1. So it goes through the point negative 1, positive 1. If x is negative 2, the absolute value of negative 2 is also positive 2. And so on. So it creates a pattern that looks like this. So the basic shape here is a V for the absolute value of x. So you should know what these graphs look like so that you can just sketch them in your sleep. That way, when we want to sketch graphs that are similar to these, it'll be much easier if you know where to start, what the basic shape or starting shape is. And that's what we're going to do now. So first I want to go back to, in your notes it should be page 44, and look at how the graphs, or if it's not 44, close to 44, but look at how the graphs of f of x equals 3x and g of x equals 3x minus 4 are related. Okay, I'm going to flip back there. Okay, this is from section 8.1. Here are the graphs of 3x and 3x minus 4. Now remember, if you look at these, what we talked about is how the graph of g of x equals 3x minus 4 is directly 4 units beneath the graph of 3x. All of these values, see these arrows in green? All of those values are shifted 1, 2, 3, 4 units down. 1, 2, 3, 4 units down exactly. So all the y values get shifted down 4. That's what that minus 4 does. Okay, so if you have a function and then you tack on to the end of that function a plus a number or a minus a number, that's going to shift your original function directly up or down on the graph. Flipping back to where we were, okay, we can interpret this now. If your original function is, say, f of x, just some general f of x, and g of x is very similar to f of x, in fact it's the same except there's a plus a number added on to the end, then that's going to shift f of x up, rather g of x is the same as the graph of f of x, but it is shifted up k units. And if it has a minus a number like this one, 3x minus 4, that shifted the graph down 4 units. So in this case, g is the same as f of x, but shifted down 4 units. In this, or k units more generally. Okay, so with that, without plotting points, let's sketch the graph of both f of x equals x squared and g of x equals x squared minus 1 here on the same set of axes. Okay, I'm going to graph f of x equals x squared in black. That's the one that we already know the basic shape of. Really, the main points you ought to know are 0, 0, 1, 1, and 2, 4. And of course, the fact that the negative values are the same. So here's the graph of f of x. Now if we want to graph g of x equals x squared minus 1, we take all these y values and shift them straight down 1. So what I do is take a few y values, shift them down 1, and plot those. So that's shifted down 1, that's shifted down 1, down 1. The other point we had was 2, 4. So if we shift it down 1, it'll go through 2, 3. And then we can fill in the graph from there. So this graph looks about like this. So there's the graph of g of x. It's the same shape of f of x as f of x, just shifted down 1. So you don't even have to plot points to graph this function if you know that the shape of x squared and you know that the minus 1 tacked onto the end makes it go down 1 unit. Saves you a lot of time in graph sketching. Let's do a similar example. Without plotting points, so no t-charts, sketch the graphs of f of x equals square root of x and g equals the square root of x plus 2. So we'll start with f and the square root of x. Now the points I'm going to plot are 0, 0, 1, 1, and 4, 2 because those were the easy points. So there's f of x equals the square root of x. And now I want to graph g of x equals x squared, or square root of x plus 2. So we shift all these points directly up 2. Up 2, up 2, up 2. I'm just doing those few points that I picked out. And so we automatically know the graph of g of x looks like that. Okay, we didn't have to plot a single point to do that. Alright, next, for this one we are going to have to plot some points because we haven't done one like this. And we're going to look at a different kind of shift. So what I want to do is first make a t-chart here to graph both of these functions. So first we'll graph the absolute value of x, and then we'll graph the absolute value of x plus 2. Now this is not going to shift it up 2 because the plus 2 is inside the absolute value. It's not just tacked on to the end of the function. Okay, if you had g of x was equal to absolute value of x plus 2, that would shift the graph of x up 2. But this plus 2 is inside the absolute value, so it's not going to do this, it's going to do something different. So we need to plot some points to see. Let's choose a few negative values. Let's go with negative 4. If x is negative 4, the absolute value of that is 4. And negative 4 plus 2 gives you negative 2, and the absolute value of negative 2 is 2. Let's try negative 3, so we'll get 3, and negative 3 plus 1 is negative 1. Its absolute value is 1. Okay, this gives us enough points to plot. I'm going to graph f in black again. So absolute value of x, we know, technically I didn't need to plot these points because we already know their values. It's a V shape. The right half has a slope of 1. The left half here has a slope of -1. Then g of x is, let's see, let's plot these points. It goes through -4, comma 2. Goes through there. Goes through -3, comma 1. -2, comma 0, -1, comma 1, 0, comma 2, 1, comma 3, 2, 4. Okay, and you get the idea from here that if you kept plotting points, it's going to go up in that direction, and it would go up in that direction as well. So g of x is the same as the graph of f of x, same shape, except it is shifted left 2 units. Notice I said left 2 units. So this is interesting. Having a +2 made it go to the left. Okay, and it is backwards from what you would expect. That's exactly what happens. So if there is a plus a number inside the function operation, whether that's taking absolute value or squaring, that's going to be a shift left. So g of x will be the same as f of x, shifted left, h units. And the opposite will happen if you have a minus on the inside. If you have a minus on the inside, g will be the same as f of x, but shifted right h units. Okay, using that information, let's use everything we've done so far to sketch a graph without plotting points of both f of x equals x squared. Okay, that one we can do very easily. And g of x. Now g of x is equal to x plus 2 all squared minus 1. It looks scary, but it's really not. Now this plus 2 is added inside the parenthesis, inside the square. So that's inside these parentheses, and it's got a positive number. So it's going to shift it left 2 units. And then the minus 1 here is really just tacked on to the end of the function. So that's what we did up at the beginning of the section. That's going to shift it down 1 unit. Okay, so how do you plot it? You take the few points that you've plotted, we've got 5 here, move them left 2, down 1, and then we'll connect the dots. So here we go, left 2, down 1. From here, left 2, down 1. Okay, so the graph of g, it looks like, will do something like this. And I can graph that very easily without even plotting points. Okay, let's look at one other type of what's called a transformation, and that is reflection. Okay, the graph of the negative of f of x is the same as the graph of f of x, except it will be reflected about the x-axis. Okay, this horizontal axis, remember, is your x-axis. So sort of view it as like a mirror line. Okay, what we're going to do is flip a graph over that. So for example, f of x equals x squared. Well, you already know what that looks like. Goes through 0, 0, 1, 1, negative 1, 1, and 2, and negative 2, comma 4. So here is f of x. Now the negative of f of x means take the negative of those y values. So if x was 0, it would still be 0. But if x was 1, you would square the 1 to get 1 and then multiply by -1, so it would be down here. Notice that's exactly opposite the point above the x-axis. If x was -1, you would square that to get +1, then multiply by that negative, so we'd still be down here. If x was 2, we'd have 2 squared times -1, so -4. Notice that's exactly opposite from that point, and the same thing over here. So these two are reflecting the reflections of each other over the x-axis. So if there is a negative out into the front of the whole thing, that will reflect it over the x-axis. Okay, negative out in front of the function reflects it over the x-axis. So now let's do one that combines everything that we have done so far. So one thing at a time. Now there are lots of things being done to this and the order does matter. So how you get the order is, imagine, okay, if I plugged in a number for x, and what's the order that I would do those things to x in? So for example, let's just do this as we go. Let's just find h of 1. So plugging that in. Okay, the very first thing you would do to that 1 is you would subtract 3. Therefore, that's the first thing we're going to handle. Now that -3 is inside the square, not outside. Okay, if it was outside the square, it would look like this, x squared plus 3, which would be a vertical shift. But it's inside the square, so which is like this. So it had plus 3, therefore it's going to shift it left 3 units. Because it's, oh no, it has a -3, I'm sorry. Therefore it's going to shift it right 3 units because it's got a minus a number. So right here, that -3 is going to shift it right 3. Actually, let's put that over here in the order we do them in. So first we'll shift the graph of x squared. I know we start with x squared because we have a square there. Right 3 units. So we'll start, before that we start with y equals x squared. Then we shift it right 3 units. Now after we do that, okay, the next thing that you do is you square it, which doesn't have any effect on translating the graph. But then the next thing you do is you multiply by that negative right there. So next we multiply, we handle this, we handle the negative. So that negative being out in front of the square is like this. It's out in front of the whole thing. Therefore, it's going to reflect the graph over the x-axis. So that's going to reflect it then over the x-axis. And then lastly, the last thing you do is you add 2 out here at the very end. That's last. So the last thing we'll do is shift it, because that just hangs out on the end, that's a vertical shift. It's got a plus, so it's going to go up 2 units. Okay, so let's start with y equals x squared. Just start with those 5 dots that we know are on the graph. Okay, so then I'm going to just draw it in sort of dashed lines here until we get to the final product. So the next thing we do is we shift it right 3 units, so 1, 2, 3. So it's going to look, I'm just taking all of these dots and shifting them right. Here's this dot, should move them right, 1, 2, 3. Now I'm going to sketch this one in as a dash line because we're not done. This is just the first step. And next then we're going to reflect it over the x-axis. Well, here's the x-axis, so it acts like a mirror. So all of these points get reflected over it. This point up here is 4 units above the x-axis, so now it's going to be 4 units beneath. And then the last thing we do is we shift it up 2 units, and that will be our final graph. So I'll shift this thing in orange. Up 2, take that point, go up 2, and up 2. So here is the final graph. This is h of x. And let's check, okay, because we did a lot of things here and there's definitely room for error when you do that. So let's plug in a point or two into h of x up here and make sure that they are plotted in the correct places on our graph. Actually, we've already plugged in 1 point, so we can check that. H of 1 should be at -2. And if you look at this, it goes through 1, -2. That is a point on the graph. So that right there is pretty much confirmation. Let's plug in one more point. If we plug in 3, we should get 2. So let's find h of 3 down here. It would be the negative of 3 minus 3 squared plus 2. 3 minus 3 is 0. So 0, that goes away. You do get 3 comma 2. So it looks like this is the correct version of h of x. And we didn't have to plot any points in order to get the graph because we knew how these things being done to x squared transformed the graph. Okay, so that's it for transformations. Next, let's talk about piecewise functions. This is really a different topic here. A piecewise function is interesting. It has different graphs for different parts of its domain. So it's made up of pieces of other graphs. You'll see what we mean when we do an example. Okay, the rule, in other words, or the rule is referring to this thing right here. This is the rule for h of x. It's what is h of x equal to? Okay, so the rule for a piecewise function is actually different for different parts of its domain. Okay, and we're going to start by looking at an applied piecewise function because I think it will make a little bit more sense this way. So here's an example that you can all relate to. Movie ticket prices are different for different age groups. Okay, so the function for the movie ticket prices would assign different price values for different age groups, meaning different y values for different domain intervals. So I'm treating age as an x value here and price as a y value. So first what I want to do is just graph this movie function. Okay, so age will be on our x-axis. Down here, this is age. And this will be price up here. Price is on the y-axis. Okay, so if the age is between 0 and 12, it's $5. If the age is between 13 and 54, it's $9. And if your age is over 55, you're going to pay $6.50. So we need to split this age axis up into, we need to go out to at least 60 to include 55. I'm going to go even a little further than that. So when you do this, each tick mark is not going to represent 1. So let's count how many we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 tick marks. Now I'm going to say maybe if I did 5 per tick mark. So 14 times 5, let's see what that is. 14 times 5 is 70. That seems like a pretty good domain. It would go from 0 to 70. So I'm going to let each tick mark represent 5. Now you don't have to label every single tick mark, really only the important ones. I've gotten past that change, so then I can just skip over to where it changes at 55. So at 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, label that, and 55. And beyond that, it's pretty easy to figure out. Now the y values go from 0 to $9, so we can just do those by ones. That'll be pretty easy to do. So we'll go $1, $2, 3, 4, 5 I want to label because that's an important value. 6, 7, 8, and 9 is an important value. Okay, so now let's graph the function. All right, if your price is between, or if your age is between 0 and 12, you pay $5. Now it does get a little tricky in here. You pay $5 if your age is, so you pay 5, from the time you're a newborn all the way up to the time you're about 12. Now 12 is about right in there. There's 12. Now when you're, actually I'm going to erase that, because when you're 12 and a half, how much do you pay? You still pay $5. When you're 12 years old and 355 days old, you still pay $5. The price doesn't jump up to 9 until the day you turn 13 years old. So the price doesn't actually jump until right here at 13. That's where it jumps up. So we're paying $5, $5, $5, all the way out to 13. Then we have an open circle there because the second you hit 13, it jumps up to $9. But until the day before you're 13, you're still paying that $5. Then you pay $9 all the way until you're 54 years and 355 days old, which is right up to 55. And then at 55, it will jump down to $6.50. So you pay $9 if you're that age, and then the second you turn 55 and older, you pay $6.50 right there. Okay, now this is a piecewise function because, as you can see, there are 3 pieces. And it's just defined differently for different parts of the domain. There's not one formula like an x squared or something that will get you these y values. You just have to say, well, if your x value is between 0 and 13, you pay 5. If your x value is between 13 and 55, y is 9. If your x value is greater than 55, y is 650. So that's a piecewise function. Now what I'd like to do is write it in function notation so you can see how this works. In function notation, you would say f of x, or whatever the name of the function is, and then you put a big open curly brace, and that splits the domain up into 3 separate, well, however many separate parts. In this case, we're going to have 3 separate parts. So you'll need 3 lines here. Now the first part is that y is, remember f of x is y, so y equals 5. It equals 5 if x is between 0 and less than 13, meaning basically if x is less than 13. Okay, because it's obvious in this case that x has to be bigger than 0. But you could go ahead and say, and x is greater than or equal to 0. But that's obvious because no one is less than 0 years old. And next, y changes. Y is all of a sudden changes to 9 if x is between 13 and 55. So you say f of x equals 9 if x is greater than or equal to 13 and x is strictly less than 55, because the second you turn 55, y is equal to 650. So this is what this function would look like in function notation. So this is how you write a piecewise function. And this also sort of explains how you read a piecewise function as well. So here's a different piecewise function. This one's determined by x's. F of x is defined by 3x plus 8 if x is less than or equal to negative 3. It's defined by y equals to negative 2x if x is this. Let me rephrase this one because we haven't learned this notation yet, but really this means if x is between negative 3 and 1. But you could rewrite that as if x is greater than negative 3 and x is less than 1. And then the last one is y is defined by x squared minus 3 if x is greater than or equal to 1. So what I want to do is find a few y values. I want to find f of x when x is negative 5, when x is 0, and when x is positive 5. So if I want to find y when x is negative 5, the first thing you have to do is figure out, well, which part of the domain is that in? Is negative 5 less than or equal to negative 3? Is it between negative 3 and negative 1? Or is it greater than negative 1? And of course, negative 5 is less than negative 3, so that puts us into this first category here. So f is defined by 3x plus 8. So we have 3 times x, which is negative 5, plus 8 in order to find f of negative 5. And then you just compute the numbers. So negative 15 plus 8 is negative 7. Or to find f of 0, so you don't go looking at the left part of the graph first. The first thing you look at is over here to the right. You're looking at the domains. So you say, where does 0 fall? Is 0 less than negative 3? No, it's not. Is 0 greater than 1? No, it's not. So is 0 greater than negative 3 and less than 1? Yes, it is. So we're in this middle piece. So f of x is defined by negative 2x, which would be negative 2 times 0. Oops, negative 2 times 0, which is 0. And then the last one, let's find f of 5. So you figure out where in the domain 5 falls. 5 is not less than negative 3. 5 is not less than 1, but it is greater than 1. So y is defined by this part, x squared minus 3. So you have 5 squared minus 3. That's 25 minus 3, which is 22. So that's how you find function values. And you've seen how you graph a piecewise function, but now let's practice graphing, okay? Now that you have an understanding of what this actually in fact means. All right, so let's graph g of x is equal to negative 3x if x is less than 2, or x plus 3 if x is greater than or equal to 2. So first we split up the domain. You say, okay, and by the way, I recommend doing this in pencil because you may have to erase part of your graph. So you say, okay, it's defined by, let's write it out in words. G is defined by y equals negative 3x if x is less than 2. Well, so you have to figure out where is x less than 2. Here's your x-axis. Let's just go with the tick marks being equal to 1. So there's 2. If x is less than 2, that means you're over here, less than 2, to the left side of 2. So for all the x values less than 2 over here, we're going to graph y equals negative 3x. Okay, so graph of y equals negative 3x has a slope of negative 3, and we do need a point on it as well. It goes through 0, 0, if x is 0, y is 0. So it goes through 0, 0, and it has a slope of negative 3. So I can go, and remember slope, let's review here. Slope is rise over run. Negative 3 can be thought of as negative 3 over 1, which would be down 3, right 1. So from here I can go down 3, right 1. I'm still to the left of 2, so I can go ahead and plot that point. In fact, I can even do one more. I can go down 3, right 1. But now it's only defined by negative 3x if x is strictly less than 2. Therefore, I'm going to need an open circle there because it's not defined at 2 by this function, but it goes right up to 2. Okay, and then to get more points, let's go up 3 and left 1, up 3 and left 1. And here's the graph of, fill in the blanks here, draw in between the points. Boy, that's tough. That's supposed to be a straight line. Really hard to draw on this thing. So that is y equals negative 3x there. But we only drew it for x values, as you can see, that are strictly less than 2, because that's where it's defined. And then we graph x plus 3 if x is greater than or equal to 2. So that's if your x values are on the right side of 2. Y is defined by x plus 3. So let's plug in 2 to that. See what we get. If x is 2, we would have 2 plus 3, which would be 5. So it's going to go through the point 2, 5, right there, and it's a closed circle because it is defined when x equals 2, it is defined by x plus 3. If x is 3, we would have y equals 3 plus 3, or 6. And as you can see, this line, it's a line with a slope 1 and a y-intercept of 3. Now we can't draw in the y-intercept because that's less than 2. That's on the left side. But we can use the slope at this point. So we go up 1 over 1, up 1 over 1, and so on. So there's not a lot of room here to graph this one. It's going to look like that. So that part of the graph is y equals x plus 3. And it's defined only for x greater than or equal to 2, because that's its domain. Alright, and I know these are challenging, so I definitely want you to give this one a try on your own first. Make sure you're getting the basics, and then watch me and we'll do it together. Okay, this one is split up when x equals 0. So it's defined by y equals 3x plus 4 if x is less than 0. So here's the x-axis. Here's where x equals 0 is right there. It's defined by y equals 3x plus 4 to the left of that where x is less than 0. So over here on this half of the graph. 3x plus 4 has a y-intercept of 4. Now I can draw it, but I must put an open circle there because it's not defined at 0. It's only defined for x less than 0. And then it has a slope of 3. Meaning, okay, we can't go up 3 over 1 because that would put us to the right side of 0. Okay, so y equals 3x plus 4 is the one I'm working with here. The slope, although it is 3, and I would go up 3 over 1, you can also think of this as negative 3 over negative 1, which would be down 3, left 1, which is how I'm going to do it. So from here we'll go down 3, left 1 to get the next point. Down 3, left 1, down 3, left 1. Okay, there's plenty of points there. And then you just sketch in that line. Okay, so there's the part of the line y equals 3x plus 4, and it's only given that graph on the left side of 0 because it's only defined for x less than 0. Now let's graph the other half, which is for x greater than or equal to 0. So for these x values, we graph y equals negative x plus 2. So let's start at the y-intercept. It is defined when x equals 0 by this function. So when x equals 0, y would be 2. So I'm going to put a closed circle there. And then it has a slope of negative 1. So from here I can go down 1, right 1, down 1, right 1, and so on to get the graph of it. So there is y equals negative x plus 2. Okay, one thing you can do to check, and I see this often, is people draw functions, or they'll just rather sketch both of these without looking at the domains, without looking at where they actually define. So if you sketched both functions, okay, this is wrong, but it would look something like this. You'd have that, and you would have that. And the first thing I see here is this is not even a function because it doesn't pass the vertical line test. Boom, right there you've got 2 y's. Right here, 2 y's the whole way. So that is not correct. So always check to make sure that you in fact actually have a function graphed, okay, not something that's not a function, and make sure that your domain is correct. Okay, that's it for piecewise functions, and that's actually all for Chapter 8. So next we will start up on Chapter 9.